Okay, so let's start with the formal lecture. I'll share my screen and here is the slides. And as I said, the lecture will be delivered jointly by me and Ma'am Sumaya Harun. So today's topic is properties of Z transform. And the outline of my presentation is that we will start with the revision of Z transform, the basic Z transform formula, and different sequences, their Z transforms, and I'll end up with a table of different Z transform pairs. Then the concept of region of convergence that you have already studied, but we'll do some examples and reiterate it further. And finally, the properties of Z transform. So Z transform is a method for representing discrete time signals and systems as a superposition of complex geometric or exponential functions. As you already have studied the discrete time Fourier transform of a sequence x of n, so that sequence x of n, once you take its Fourier transform, it is x of e raised to power j omega, which is equal to n is from minus infinity to infinity x of n e raised to power j omega n. Okay, let me annotate. Right. So in case of the discrete time Fourier transform, x of e raised to power j omega is able to handle stable systems only. So this is important. We stamp it. And for the case of Z transform, you can handle some more systems, which x of e raised to power j omega cannot handle due to the divergence. So wherever the systems are unstable, you cannot take their Fourier transform, and hence you need to rely on some other kind of transform such as Z transform. The Z transform analysis formula is given by equation 3.2, and you can see that for Z equal to R e raised to power j omega, so Z equal to R e raised to power j omega, you have xr of e raised to power j omega, which is summation is now from n equal to minus infinity to infinity x of n z of minus n. So if you replace z with r e raised to power j omega in this equation, then obviously what you will get is x of n e raised to power minus j omega n and another term r of minus n. So this r of minus n is a handle which you can use later to actually identify whether the system based on the value of r is stable or not. Right. So the Z transform represents the condition of convergence of xr of e raised to power j omega in terms of the region of convergence. So जहाँ पे region of convergence उसका होगा जहाँ पे xr of e raised to power j omega converge करेगा based on the value of r, तो वो एरिया वहाँ पे x of z यानी z transform exist करेगा. In other words, x of z is defined for a region in Z called ROC for which the sum exists. राइट। तो जहाँ सम एग्जिस्ट कर रहा होगा वहाँ रीजन ऑफ कन्वर्जेंस होगा। एग्जाम्पल ये है that if you have x of n is 1.1 of n u of n, so अगर हम देखें इसको, अगर हम ये देखें कि इसका क्या फोरियर ट्रांसफॉर्म लिया जा सकता है, तो नहीं लिया जा सकता, बिकॉज a इसके केस में 1.1 है। सो चूंकि ये 1.1 है तो its Fourier transform, the C-type Fourier transform does not exist, but if you want to take its Z transform, that exists. Because if you plug in R e to the power j omega and you take and it is a value which is greater than 1.1, so Z is greater than 1.1. So basically this is a causal system or a causal sequence. So 1.1 of n, u of n is a causal sequence, और 1.1 के बाद ये रीजन ऑफ कन्वर्जेंस है इसका, जो कि ये डैश लाइन से शो हो रहा है। सो 1 इज अ यूनिट सर्कल, और फिर उसके बाद 1.1 पे देयर इज अ पोल। सो 1.1 के बाद तो रीजन ऑफ कन्वर्जेंस जो है उसमें पोल शामिल नहीं होता, लेकिन पोल के बाद जो है 1.1 onwards 1.1 you have the region of convergence. So another final thing is that if for a sequence the Z transform includes x of e raised power j omega. Okay, so let's suppose कि मेरा पोल यहाँ पे लाया करता, let's suppose 0.9 पे लाया कर रहा है, तो इस 0.9 के बाद अगर रीजन ऑफ कन्वर्जेंस है, एंड इज अ राइट हैंड साइड सीक्वेंस, सो 0.9 ऑफ n u ऑफ n है, सो इसका मतलब है कि यूनिट सर्कल जो है वो इसमें इंक्लूडेड है। सो इन दैट स्पेशल केस you will have you will have x of z, which also includes the discrete time Fourier transform. Okay, so r equal to 1 उसमें शामिल है, whereas the pole is a value less than 1. मगर अगर let's suppose exactly pole पे pole जो exactly unit circle पे है, in that case you would not have the Fourier transform. x of z के केस में Fourier transform. Okay, the z transform in our course is also called a bilateral z transform, and it is given by the formula 3.2. The bilateral z transform is a two-sided z transform, which is different from a unilateral z transform or a one-sided z transform. So one-sided z transform क्या होगा? That assumes that x of n is 0 for n less than 0. Okay, so हम ये assumption नहीं ले रहे, हमारा two-sided z transform. Let me show you in this slide. I've shown common z transform pairs. जैसे डेल्टा ऑफ एन है, सीक्वेंस डेल्टा ऑफ एन है, ट्रांसफॉर्म जी ट्रांसफॉर्म उसका 1 है, and the region of convergence is all z. Okay, so all complex values of z वो region of convergence है। If the sequence is u of n, then the z transform is 1 over 1 plus z inverse. Okay, so this is the z transform of u of n, and z is greater than 1 in that case. So 1 is not included in the region of convergence. इसका मतलब ये है कि ये जो है इसका फोरियर ट्रांसफॉर्म एग्जिस्ट नहीं करता। Now if you have minus u of minus n minus 1, the z transform is the same for this. Okay, वो again 1 over 1 minus z inverse ही है, but the region of convergence is different. Z mod is less than 1 in that case. If you have delta of n minus m, then you have the Z transform of this sequence z of n minus m as z of minus m. So जब z of minus m होगा, then there are two possibilities. या तो m की value positive में है. So if the value of m is positive, जो region of convergence है वो सारा का सारा शामिल है except z equal to 0. Okay? क्योंकि इसमें पोल जो है वहां वो 0 पे लाया कर रहा है, तो इसलिए z equal to 0 पे पोल है और रीजन ऑफ कन्वर्जेंस वहां तो नहीं है. जहां पोल होगा वहां रीजन ऑफ कन्वर्जेंस नहीं होगा. Whereas if m is less than 0, in that case the pole lies at infinity, and all of the region, all of the z is included in the region of convergence except infinity. Similarly, ये examples आपने देखी होंगी 3.1 and 3.2. वहां हमने देखा था कि a of n u of n, which is a sequence, a right hand sided sequence का z transform 1 over 1 minus a z inverse है, and the region of convergence in that case is z is greater than a mod. Once we saw example 3.2, we saw that a sequence which is a left hand side sequence such as this one, minus a of n u of minus n minus 1, तो उसका z transform भी same है. But the thing which differentiates between these two transforms is the region of convergence. So in that case, z is less than a. So a is not included. A is the pole. A is not included in this unit circle in the region of convergence. But since it is a left-hand sided sequence, so इस pole से left side पे या इस pole के अंदर till 0, you have the region of convergence. Okay. Some more z transform pairs are following. जैसे n a of n u of n है. So for that you can use differentiation property, जो हम आगे भी पढ़ेंगे और फिर उसके अलावा इसकी मुख्तलिफ एग्जाम्पल भी देखेंगे. तो उसमें जो ट्रांसफॉर्म है that is a z inverse over 1 minus a z inverse whole square, and z is greater than a in that case. Similarly, minus n a of n u of minus n minus 1. So इस केस में भी z transform same है, but the region of convergence is different because it's a left hand sided sequence. So z is less than a mod. Now if you have cos omega naught n u of n, you can use this sequence. So again, this is the right hand side sequence. Cos को आप exponential j omega naught n plus exponential minus j omega naught n divided by 2 भी लिख सकते हैं, and you can use you can expand that to find out that the z transform is this this value, and z is greater than 1 in that case. Okay. Again, for sin omega naught n, the value is different, and z is greater than 1 in that case as well. So basically ये स्टेम कहाँ से करता है? ये स्टेम करता है u of n का फोरियर ट्रांसफॉर्म. सो u of n का फोरियर ट्रांसफॉर्म ऊपर देख चुके हैं. इट इज 1 over 1 minus z inverse. तो उसका जो रीजन ऑफ कन्वर्जेंस है that is z mod is greater than 1. तो इसीलिए cos और sin के केस में the region of convergence z mod is greater than 1 for both cases. Now if you have r of n cos omega naught n u of n, then obviously that will be replaced by r, and same is the case with sine. Finally is the a sequence which is a finite sequence. जैसे a of n है, start होता है 0 से n minus 1 तक जाता है. In that case, the transform and 0 otherwise. So the transform is given by this expression. So 1 minus a of n z of minus n over 1 minus a z inverse, and z is greater than 0 in that case. So इसको हम example 3.6 में देखेंगे कि ये कैसे z transform हमें मिला है. So let me just shift um, to the to to the book itself, और उसमें examples जो हैं वो initial हम देख लेते हैं, और उसके बाद इस finite duration sequence के लिहाज से भी example देख लेते हैं. Right. So let me share the screen again. Okay. So this is example 3.3. You can see that you have x of n, which is the sum of two sequences, 1 over 2 of n u of n plus minus 1 over 3 of n u of n. So ये दोनों right hand side sequence है. That's why you have this pole at 1 over 2 and it is a value less than 1. So normally a unit circle is represented by uh, solid line, whereas wherever the pole is, you represent it by a broken line. Now in this case, you can see that there is a 0 at 0, that equal to 0. And then another sequence is minus 1 over 3 of n u of n. So minus 1 over 3 is a pole at minus 1 over 3, and it is a value less than 1 over 2. So this is one thing. Let me. So अगर आप इसको jointly लिखना चाहेंगे, obviously you take the z transform of one sequence and you take the z transform of another sequence. तो collectively आप इसको दोनों की addition हो रही है, तो इस तरीके से लिख सकते हैं. And by taking the LCM, you can find that these are the two poles. This is the 0. So the 0 is at 1 over 12. There is a pole at 1 over 2 and another one at minus 1 over 3. अब क्या है कि if you take the z inverse common in both the denominators and the numerators, तो आपको यहाँ एक z extra मिलेगा. That z means that there is a 0 at z equal to 0 and there is a 0 at 1 over 2, 1 over 12 as well. Okay, so let me show you this diagram कि 1 over 12 और 0 पे दो zeros हैं. There is a pole at 1 over 2 and another one at minus 1 over 3. So अब हमें ये देखना है कि region of convergence क्या है. तो region of convergence वो है जिसमें जो दोनों का ओवरलैप है. तो जो अकॉर्डिंगली minus 1 over 2 भी extend कर रहा है towards infinity, and similarly minus 1 over 3 का mod ले लें तो वो भी pole के outside this pole is the region of convergence because it's a right hand side sequence. तो दोनों का जो intersection है वो half से onwards है. That's why you have the region of convergence starting from 1 over 2. It doesn't include 1 over 2, but so that's why collectively what you can write is that z mod is greater than 1 over 2. So after this example, we can go on to do another example. Now in this case, example 3.4 says that you have the sequence minus 1 over 2 and u of n. It is a right hand side sequence, but the and similarly, okay, let's not go, because इसमें कोई खास चीज नहीं है. डायरेक्ट हम पेयर्स के लिहाज से विदाउट सॉल्विंग इट हम इसको लिख रहे हैं. तो दैट इज अ कन्वीनियंट वे टू अस, बिकॉज अगर हमें टेबल पता है तो हम इससे लिख सकते हैं. But now if you have minus 1 over 3 of n u of n, which is a right hand side sequence, and minus half of n u of minus n minus 1, so in this case you have a left hand side sequence. So right hand side का direct हमने लिख दिया, राइट हैंड साइड का हमने डायरेक्ट जी ट्रांसफॉर्म लिख दिया, लेफ्ट हैंड साइड का भी लिख दिया और उसका रीजन ऑफ कन्वर्जेंस भी लिख दिया. सो रीजन ऑफ कन्वर्जेंस के लिहाज से ये जो है ग्रेटर देन 1 over 3 एंड ये लेस देन 1 over 2 है. नाउ So जब हम दोनों को collectively लिखेंगे तो you will see that again the Z transform is the same for both of them, but the region of convergence is between 1/3 and 1/2. Okay, so जो दोनों का annular region है या disk type region है वो हमें नजर आएगा because 1/3 is a value के जिसके 1/3 जो है वो outside 1/3 is the region of convergence. Okay, so इसके बाहर region of convergence है और इसके अंदर because it's a left hand side sequence, so half के left side पे region of convergence है, इन दोनों का annular region जो है वो region of convergence होगा. Okay. So after doing this example, I hope काफी clear हो जाएगा कि अगर one is a right hand side sequence, another is a left hand side sequence, तो दोनों के लिहाज से जो disk region है वो क्या होता है. Let me start by this example. So this example is finite length sequence. जो हमें table दिया हुआ था उसमें last वाली pair है, the transform pair. So x of n is a of n for 0 less than equal to n less than equal to n minus 1. So and 0 otherwise. So if you take the Z transform of this, what you get is instead of minus n equal to minus infinity to infinity, you can write n equal to 0 to n minus 1, a of n, z of minus n. And because this formula is using equation 2.56, जिसमें हमने देखा था कि कैसे एक ज्योमेट्रिक सीरीज को सम किया जा सकता है if it is starting from 0 to a finite value n minus 1. So in that case, what you get is 1 minus a z inverse this power n over 1 minus a z inverse. So this is the final value that you get. Now here you have this pole z of n minus 1 at z equal to 0. So there are n minus 1 poles at z equal to 0, and also you have a pole at z equal to a. Similarly, z of n minus an means that you have number of zeros. Okay, so all these zeros are distributed at around a. Okay, so जो circle है a का उसके ऊपर ये zeros lie करते हैं. So this is so n roots of the numerator polynomial are z of k equal to a is for j 2 pi k over n for k equal to 0 to n minus 1. Because a पे lie कर रहे हैं तो आप ये देख सकते हैं कि ये let's suppose for example हमारे पास 16 जो है ना वो poles हैं, तो 16 zeros होंगे 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. तो यहाँ पे 16 zeros हैं जो कि इस सर्कल पे लाया करें एक के रेडियस का सर्कल है. ओके, एंड देयर आर 15 order poles at z equal to 0. Also, चूंकि हमने ये देखा था कि you also have a 0 at you also have a pole at z is equal to a. Okay, so n minus 1 यानी 15 पोल्स तो एग्जिस्ट करते हैं, एक और पोल जो है वो z इक्वल टू a पे भी है. तो अब वहीं पे जहाँ z इक्वल टू a की वैल्यू है वहां जो जीरो था उसको उस पोल ने कैंसिल आउट कर दिया. सो व्हाट इट एसेंशियली मींस इज कि जो रीजन ऑफ कन्वर्जेंस है, इस रीजन ऑफ कन्वर्जेंस में ये 15th ऑर्डर पोल्स तो शामिल नहीं है, बिकॉज ऑब्वियसली जहाँ पोल होता है वहाँ रीजन ऑफ कन्वर्जेंस नहीं होता, बट आउटसाइड दिस टिल इंफिनिटी यू हैव द रीजन ऑफ कन्वर्जेंस. सो एक n equal to 16 का जो हमारा फिल्टर है which is a finite duration sequence या एक finite duration sequence है हमारा, तो वो which is x of n, वो जो है उसका रीजन ऑफ कन्वर्जेंस एक्सेप्ट जीरो सारे z's पे है. Okay, right. So let's start with this. I'm going to stop this share, and I think we can pause here, and then from the next slides we'll start of new topic.